Good morning. All right, let's take a look at lesson 5.3 on your digital classroom. If you want to open this up, go to your classwork. We will be on lesson 5.3, so we can open that up. A few things that would be very helpful today in particular, we might use our Desmos calculator. So I'd recommend you open that up. I'm going to copy here this formula chart. We're going to be using the formula chart here. So let me put this in between number 3 and number 4. Let me actually back up. There's numbers here, as we know, 4 things to accomplish every lesson. Number 1, the fact that you are listening to me means you're taking care of it one way or the other. I have one kid sitting in classroom. That'd be the recommended, highly recommended. I have, it looks like 19 people currently on Zoom, probably more here in a few minutes. And who knows how many in the future checking in on through YouTube. But either way, those are the 3. So you're taking care of number 1 there. Make sure you do your attendance. So take that link right there, click that one, fill out your attendance, or you can scan this QR code in a moment. Finally, you can open up your lesson. Bell ringers will submit as we go. You can open that up, but these 3 documents in particular, actually today, I think we might be using all 3. So I'm gonna open up the formula chart. And instead of me clicking this one, I copied and pasted one, so I don't have to go back and forth between tabs, a unit circle. I'm going to open up that unit circle here. If it opens, there it is. And we will use unit circle today. Okay, so I think I got everything we need. So I got Desmos calculators. Oops, I don't think I ever clicked it. For Desmos, I'll probably be using just a blank calculator. We'll see as we go, but I'll just hit number 11 just so I can see my ratios. So number 11 has the ratios for trigonometry, and I'll just close off all this other stuff here. Okay, with that, let's get started. Number 1 here. Did I get this out of order? Oh, no, I don't know what I did. Let me delete that. I'll leave that down there for you to fill out. All right, number 1 here. It says simplify the following. Tangent times cotangent divided by cosecant. And if we remember, there was an acronym called SPOT oil that I've been using. And the first thing that the S stands for is to try to simplify. If there's anything that cancels here, or if you can factor out anything that's common. And the answer to that question is no. There is nothing in common and nothing I can cancel. So I move on. P is for Pythagorean. Specifically, you must have squares or ones, or usually the combination, ones and squares. I don't have any of those. O, I call it opposite denominator. It's technically conjugate. It's when your denominator has a 1 and a trig function, but the trig function does not happen to be squared. In this case, I do not have a 1, so I cannot do the conjugate step. Which brings me to T. Can I transform anything to sines and cosines? And the answer to that question is yes. Okay, so the easiest way first to do this, I could break it down into more steps, but I think the easiest way is actually going to be to do this number. I'm going to take my cotangent here. Do I want to do it this way? You know what I'm going to do first? I'm going to get rid of the denominator. I'm going to transform it so that my denominator disappears. I think that might help you out. So the first thing I'm going to do is I'm going to shoot this up. In trigonometry, every single trig function has a reciprocal. And so I want to shoot cosecant up to the numerator, which means I need to take its reciprocal. I'll go to the formula chart. And I'm going to make this a little larger. And I'm looking under the reciprocal identities, and I want to find cosecant in the denominator, which I see it right here. Let's see if it'll highlight for me. This formula chart doesn't always cooperate, but there it is. I have cosecant in the denominator. Cosecant in the denominator, or said another way, 1 divided by cosecant is equal to 1 times sine. There's no 1 there because it's multiplication. So 1 times sine is equal to 1 divided by cosecant. So in this case, tangent cotangent divided by cosecant will be equal to cotangent cotangent times sine. This is being divided by cosecant. It's the same thing as multiplying by sine. So let's do this right here. We'll say we have tangent. Actually, I don't need the denominator anymore, so I'll just do level. Equals tangent theta times cotangent theta times sine theta. Now that right there, we would call a reciprocal identity. Actually, I'm gonna put this so it doesn't look like that's what I did right there. All right. Now, while I'm still transforming, I'm gonna continue on this. Change things to sines and cosines. I know I can change tangent and cotangent. So specifically, sine is y, cosine's x, tangent is y over x. Thank you, Samuel. So tangent is sine, that's y, over cosine, because cosine's x. And not only that, cotangent is its reciprocal, which means cotangent is the same thing as cosine divided by sine. Now, you did not have to do it this way. Some of you might have realized that those are reciprocals, so they cancel each other out, but I'll write it this way so you can see more clearly what's about to happen. Now, both of these were called the quotient identity. Those are called quotient identities. When you change sine and cotangent to, tangent and cotangent to sines and cosines, that's called a quotient identity. And since I did it twice, I will say it plural, identities, because I did both of them. So what can I do from here? I can notice that this sign and this sign cancel each other out. They're factors because these are multiplying, dividing, so you can cancel factors. So that sign and that sign will cancel each other or simplify. And these cosines will simplify, and which means I am left with sine theta. And that was after doing a little algebra there. If you were naming that step would be called algebra. And so lo and behold, we find out that tangent theta times cotangent theta divided by cosecant theta equals sine theta. Now, something we didn't get to live last class, because I just run out of time for most of them, is on example 6, I would have shown you that if you graph these functions, you can tell whether or not it's right or wrong, or identity is the word, if it's an identity or not, by if you graph the left side of the equation. And so with Desmos, I'm going to use an x instead of a theta here, times cotangent x all over cosecant x. And notice it's not graphing. That's because whenever trig multiplying in Desmos, I forgot I need to use parentheses. Not only that, let me change to radians. Graphing, you wanted to graph in radians, it looks better. So as you can see, that's what the graph appears to look like. Let's check out y equals sine x. I only have one trig function, so I can go without the parentheses. And you notice that they look exactly the same. I can even help you out a little bit more. I wanted to do that, make that one a little darker, and I'll make that one dotted. And you can see that they overlap each other perfectly. At least I think you can see that. Hopefully you can see that. Maybe I do it this. There you go. So it is in fact correct. That is a true statement. That's how I'll put that check mark. We checked it. Okay. So let's check out number 2 here. Number 2 says, during a scouting exercise, Alex leaves camp and hikes 4 miles northwest. He then turns and hikes 8 miles due north. Karina leaves camp and plans to hike on the same direct path to Alex's new position. What angle from the positive x-axis should Karina hike to the nearest 10th of a degree? And so this question is a throwback to chapter 4, and specifically it's a chapter 4 application problem. If you remember from chapter 4 where is it? Chapter 4, and right at the very end before the test, I had this chapter 4 applications. This is a throwback from that lesson, because in that lesson, I talked a little bit about north, south, east, and west, and we learned a few things. Number 1, when you're talking about directions, north looks upward, east looks to the right, south looks down, and west looks to the left. Now, I say those words, that's how they appear. Now, if I asked you, where's Canada? If you pointed straight up towards the ceiling, you're wrong. North doesn't mean literally up from where you're sitting. North means on a map that's laid flat, upward. Okay, just make sure you know that up would get you to the atmosphere, not to Canada, for those American viewers here. Just make sure we're clear on that. I've had students when I've asked them, hey, which way is north? They point directly up into the sky. And that's not right. That's just funny. But anyways, Alex leaves camp and hikes 4 miles northwest. Now, what that means, northwest, if you're not familiar with that term, is it means it splits the difference between north and west. So it's going to go diagonal between north and west. And it's going to do this for 4 miles. I'll just say that's 4 miles. Okay. I'm just going to put a 4 there, 4, and I'll put MI for miles. So Alex first walks that distance, and then it says he turns and it goes 8 miles due north. So that's 4, then that'd be about another 4, and let's just say that's 8. So he then walks 8 miles due north. Now what due north means is from this new location, he doesn't walk to the end, he walks from this location where due north would be, which would be, again, on a map, straight up above from where he is located at that point in time. We want to know what angle should Karina hike if she were going to try to meet Alex. So Karina sets off and says, I want to walk directly to Alex. I'll make Karina green. And so what's the angle she should walk from? It says the positive x-axis. That means basically from the east. This is what we're looking for. What is that angle there? Okay, so to solve this, I notice it's a triangle. You cool with that? Triangle. And in triangles, we've learned that if you can always, no matter what type of triangle it is, if it's right triangle, obtuse, acute triangle, doesn't matter, you can always solve with either the law of sines or the law of cosines. Whoops. I was about to just write cosines. Let me say law of cosines. Now, this all comes down to whether or not we have what we call a set or a completed pair, meaning we have a side length and the angle across from it. So let's talk about what angles we do have. I know that that around here, each one of these is 90 degrees. So I do know that it's 90 degrees. And I know this amount right here would be half of that, which is 45 degrees. So let me erase this theta that we're looking for, and I'll replace it. I'll do red since that's red. We can state for a fact that that right there is 90 plus 45 degrees, which would be 135 degrees. That's the angle there. However, that's not the angle of the triangle. So I want you to know that that is a true statement, but it's going to be kind of worthless right now in our problem because we don't know how many degrees goes from here to here. And we're looking at this triangle. That is not an angle in the triangle. It's the angle from here over. So that doesn't do me good. But here's what it does do. If I came over here, I can state something very confidently. Let me add a little line. From the point we turned and went due north, here's what I can state confidently. Let me get these lined up right. Okay, what I can state confidently is on this angle, I have 90 degrees there, and this is splitting it there. I have 45 degrees there. So this angle is 90 plus 45, which would also be 135 degrees. Now I can solve my triangle. You can solve a triangle, I should have said this earlier, as long as you have 3 pieces of information, which we do now. And by the way, right angles would count as one of the 3 pieces of information. If you were looking at a right triangle, that would count. So to solve this, I have 3 pieces of information. I know this leg is 8. I know this leg is 4, and I have an angle. That's the whole angle of this part of the triangle. From here to there is 135 degrees. So since I know one angle and these 2 sides, we could solve it. Okay, do I have a completed set? No. So I'm going to use the law of cosines. So let's go over here to our calculators, and I shouldn't have closed the link. Let me open that up again. I'm going to close this link. That's the one I meant to close earlier. And when my calculators come up, I'm going to go to the law of cosines. Law of cosines, there it is. So I use this without a completed set or pair. And here's how I'm going to label this. I'm going to call this one the capital A here. This I'll label as B, and this one I'll label as C. It doesn't matter how I label them other than for my calculator, I have one angle that needs to be the A. Okay, so this is 135 degrees. We do not know little a, but I do know little b will be 8. And little c here, lowercase c, is 4. Since I don't know lowercase a, I'm going to put an x there. This tells me my length is, here's the exact, or more of a closer answer, but here it is rounded. I'm just going to say it's 11.192, just like theirs. This length across is 11.192. 11.192. Now, what does that do for me? Well, now I can turn and find this angle here. And once I find this angle here, I can subtract from 135 to get that angle there. Okay, so now let's find this angle from there to there. So I'll go purple here. To find this angle, I now can use law of cosines, but I'm going to say I know the 3 side lengths, and I'm going to solve for this angle. So since I'm going to solve for this angle, I'm going to put, I know it's the letter B here, but I'm going to switch that from my calculator to the letter A and say that's the unknown. So I'm going to treat this now as the unknown. But what I'm going to do is the side length across from it is 8. So that needs to be the lowercase a, because these two are my new pair I'm searching for. So that's unknown. This is 8. And then I put in the other 2 side lengths, which this was 11.92 now. 192, I think. 11.192. Yep. So once I put those in, I can see that angle is 30.4 degrees. I'll say 30.4 degrees. It says to the nearest tenth, so I'm going to say it's 30.4. Now that I know that's 30.4 degrees, 30.4, what we can do is solve for this little angle right here. So that angle would be 135 minus 30.4. 135 minus 30.4, which is 104.6. Okay, so let's make sense out of this whole problem here. What angle should Karina hike to meet Alex? Karina should hike 104.6 degrees from the positive x-axis. Now, and something else we learned is she should hike this many miles. So that would get her to Alex. We are going to learn in the coming days, specifically chapter 9, how to do this problem a lot quicker. So we'll learn some tricks as we go. But there's your bell ringer. With that, let's get started with the new lesson. So oh wait, I'm speaking too soon. Let's review one more, how to verify an identity. Now remember, what we can do is we can graph these two to see if they're equal to one another. But I'm going to treat it as the graph, let's just state that the graph, we believe it is the same. And so for that reason, we're going to try to verify it by proving it's true. So I'm going to use spot oil here. S step stands for simplifying. It can mean by canceling or by factoring, which in this case, I can see that there's going to be a factor here. What I'm going to do is I'm going to work on the left side because it's more complex. And so I notice both the first two terms, remember terms add and subtract, these first two terms share a secant. So what I'm going to do is I'm going to factor that secant out, like GCF style. That's what I'm doing here. It's technically called algebra on your Alex, but the more specific name would be greatest common factor. If you do a GCF, it's basically the opposite of distribution. So instead of multiplying something through a group, you're dividing something out to create a group. And so I'm dividing from both of these to create a group. So what am I left over here? Secant divided by secant is 1. And then over here, I'm left with sine squared. Now I go back to my list. So that was simplifying. I say, okay, what about Pythagorean? Do I have any ones and squares? And yes, I do. I have a 1 minus sine squared. And if you go to your formula chart, you'll notice on Pythagorean, here's the sine squared. If we needed it to be 1 minus sine squared, envision your brain. If I needed to be 1 minus sine squared, that means I need to subtract sine squared from over here. which would eliminate that sine squared, leaving me with just cosine squared. So this right here is equal to cosine squared. So I now have secant x times cosine squared. And that was the Pythagorean identity. Come back. Can I simplify? Not yet. Well, you might be able to if you know what you're doing, but I'm just going to say not yet. There's nothing in common to factor. Pythagorean, no, I just did Pythagorean. I'm not going to go backwards on that. Opposite denominator, there is no denominator. I can't do a conjugate. Can I transform anything to a sine or cosine? Yes, I can. I can transform this secant. Now, secant, what is secant? If I go to the reciprocals, so look over here, reciprocals, and I look for secant in the numerator. So right now it's not the denominator. I see secant in the numerator is equivalent to 1 divided by cosine. Or, stated another way, it's going to be, since this secant was multiplying times cosine squared, it will be cosine squared divided by cosine. So for the sake of notes, I'm going to change secant to just 1 over cosine, very simply. And then I will put this cosine squared right here that's multiplying. And so that name of that step was reciprocal identity. And you can see by algebra that that in fact would equal cosine. Exactly what we wanted to equal. So there was a bell ringer review problem that was not shown up on the front.